Welcome to another episode of Unlearning Unlicensed. In this video series, I am going through RF Elements educational content, and I am correcting the myths, misconceptions, and misunderstandings that RF Elements created so that they could sell more of their antennas. In this video, I'm talking about beam efficiency, which RF Elements describes as the most important antenna parameter. As far as I know, RF Elements is the only antenna vendor that uses beam efficiency as an antenna parameter. That doesn't make it very useful as an antenna parameter because most WISPs use antenna parameters as a way of doing product comparison, as a way of comparing this antenna versus that antenna. And if only one vendor is using an antenna parameter, that doesn't make it very useful. But you don't need to take my word for it. We can just hop right in. Here we go.
I'm Tomar Zelensky, and I'm a product manager at RF Elements and marketing manager at the same time.
So he says he's the product manager and he's the marketing manager at the same time. And I think the problem here is that he's leaning into his role as the marketing manager a little too much and his role as the product manager not enough. So the role of the product manager is to develop the products to meet the needs of the customers, whereas the role of the marketing manager is to convince the customers that these products meet their needs. And I think that you'll see with beam efficiency, it's much more marketing and much less product.
And my promise for today to you is that you will learn what beam efficiency is. Why do we actually think it's the most important antenna parameter in WISP networks? As well as you will also learn about the other antenna parameters that are usually thought or known for showing the ability of an antenna to deal with noise. So let's start. So the parameters that are usually considered relevant when speaking of the ability of an antenna to mitigate interference are front to back ratio, side lobe levels, or ETSI masks. These you most likely know or at least heard about. The one that RF Elements believe is the most important one in terms of noise suppression is beam efficiency.
So this is interesting. It says these are the noise rejection related antenna parameters. And he lists out front to back ratio, yes. Side lobe level, yes. ETSI mask, yes. Beam efficiency, sure. But he ignores beam width, especially in a point to multi-point sector antenna. Beam width is one of the main parameters that you would look at when dealing with noise. So the difference between a horn antenna and a sector panel antenna is mostly beam width. Sector panel antennas usually tend to have wide beam widths, 120 degrees or 90 degrees, maybe 60 degrees. But with those wider beam widths, you're picking up noise from the entire sector. If you have a 120 degree beam width, then you're picking up noise from that entire 120 degree sector. Now, if you have a 30 degree beam width, you're picking up a lot less noise and interference from that main lobe. So the beam width is one of the key antenna parameters that you should be looking at when thinking about noise rejection. And RF Elements totally misses that.
Beam efficiency is the ratio of the main lobe energy to the total energy an antenna radiates.
Keyword there is radiates. So he says beam efficiency is the ratio between the energy in the main lobe, the total energy an antenna radiates. There's a lot of energy that is lost before the energy radiates. There's VSWR, or return loss, which is the amount of signal that an antenna reflects back at the radio. And that is lost energy, but not accounted for with beam efficiency. There's cable loss or conduction loss, where the electrical energy is lost before it is converted to radio waves. And then there's loss within the antenna too, due to things like the radome, where the energy is absorbed by the antenna. And again, it's not radiated. So beam efficiency doesn't account for any of those losses. And what's interesting is that while focusing on beam efficiency, they dismiss other antenna parameters such as gain, which actually do account for all of those losses, because gain is the measurement of the antenna's ability to efficiently focus energy in a specific direction. It is measured relative to a perfect isotropic radiator. In other words, an antenna that is radiating perfectly in every direction. So gain will account for VSWR. It will account for cable loss. It will account for the loss of energy by the radome. Beam efficiency, although it's called efficiency, it's not measuring antenna efficiency. It's only measuring the energy that essentially leaves the antenna. It's not talking about any of the efficiency of energy before the signal leaves the antenna. And that's one reason why beam efficiency is really an incomplete antenna parameter. Certainly not the most important antenna parameter, because it doesn't account for antenna efficiency, despite the name. The other thing that's important to notice is that they're defining it as the energy in the main lobe relative to all the rest of the energy that the antenna radiates. They're defining the main lobe, the main beam, up to the first null, but they don't define the first null. So when you look at antenna patterns, especially across a frequency range, you'll notice that a lot of times the side lobes, the largest side lobes, emerge from the main lobe. At what point does the main lobe end and the side lobe begin? If you don't clearly define that, which they haven't defined that, then that's a subjective measurement. You say, well, to me it looks like this is the main lobe and that's the side lobe, but who's to say? You need to clearly define what is the first null. Without clearly defining that, then beam efficiency just becomes subjective. Who's to define the main lobe? Elements? I don't think so.
Now it says how much of the total signal energy is contained in the main lobe. As simple as that. So the maximum beam efficiency value is 100%, which is an ideal situation. That's really the ideal goal we desire.
The ideal goal we desire is not 100% beam efficiency. The ideal goal that we desire is that 100% of the radiated power is sent towards the receiving antennas. In the case of a point-to-multipoint network, sent to the stations within the sector. And in the case of a point-to-point application, you want to send that to a single point. It's not that you have it all within the main lobe. The main lobe can still be sending signal in unintended directions, particularly in point-to-point. That's most obvious in point-to-point. So in a point-to-point application, it doesn't matter if all of the signal is contained within the main lobe, if the main lobe is still sending the signal in undesired directions. And similarly, the same can be true for point-to-multipoint with a sector. So you could have a 60-degree sector, and you could have all of your stations within that 60-degree sector. But 60-degree sectors are often defined as half power beam width being 60 degrees. So there's still a lot of power within that main lobe, within that main beam, outside the 60-degree sector that is wasted power, and you're picking up extra noise from the main lobe. So beam efficiency doesn't account for wasted energy if that energy is within the main lobe. So you really have to think about the shape of the beam, not just essentially the antenna pattern, not just whether it's in the main lobe or not within the main lobe.
And the smaller the beam efficiency is, the more side lobes an antenna has. Since antenna side lobes are the direct cause of problems in WISP networks, antennas with a lot of side lobes should be avoided at all costs.
So he says antenna side lobes are the direct cause of noise in WISP networks. They're not the only cause of noise within WISP networks. Again, a lot of the noise in WISP networks is picked up within that main beam, particularly with point-to-multipoint sector application. You're going to be picking up noise from the entire sector. And you could be picking up noise from the side lobes. But the side lobes are not the only cause of noise problems on WISP networks.
The higher the beam efficiency of the antenna you use is, the better for your network and the end users of your services in the end. Beam efficiency is an antenna parameter not only to know about, but actually also factor it in when you're deciding on how to deal with the interference issues you may have in your unlicensed networks. Now here is a practical example. So this is the radiation pattern of a generic parabolic dish. And if its beam efficiency is 40%, the remaining 60% of the energy goes everywhere else. In other words, side lobes. Because any radiation outside the main lobe is a side lobe, well, obviously it must go in the side lobes. Note that all the side lobes are highlighted here, so beam efficiency includes all the side lobes an antenna has. If you want to compare two antennas in terms of side lobe performance, beam efficiency makes it extremely simple. The higher number wins. In this example, the ultrahorn on the left has beam efficiency 99%, so only 1% short of perfection. A generic dish antenna, on the other hand, has beam efficiency 40%, so the remaining 60% of the energy it radiates is in the side lobes. 99% is clearly more than 40%, and that's why ultrahorn is way better antenna in terms of noise suppression. In our opinion, the best on the market, to be honest.
So that depends again on whether the source of the noise is coming from the side lobes or if the source of the noise is coming from the main lobe. If the source of the noise is coming from the main lobe, then having high beam efficiency isn't going to help with noise. If the source of the noise is coming from the side lobes, then having high beam efficiency will help you reduce the noise. It just depends on where the noise is coming from. It depends on the shape of the beam. So it's also worth noticing that you could have much more focus on the main lobe, and you could have much higher gain on the main lobe, and then you have side lobes. Even in a noisy environment, it's quite possible that having the increased gain is going to be more helpful than reduced side lobes. So beam efficiency, although RF Elements likes to believe that beam efficiency is the number one parameter to care about with WISP application, no, you have to factor everything in. And the increased beam efficiency of the ultrahorn may or may not help with noise. It just depends on really where the noise is coming from.
But to be fair, let's also have a look at the parameters you may already know. Front-to-back ratio is one of them, and many manufacturers include it in their data sheets. So let's have a small recap of front-to-back ratio. The conventional thinking about front-to-back ratio is that if the front-to-back ratio is high, it means an antenna is good for dense collocation. So if the antennas are back-to-back and both have high front-to-back ratio, they will not interfere with each other. The reality is that high front-to-back ratio does not mean that antenna is good for dense collocation in every possible setting.
So I just find this to be a little bit disingenuous. He just said is good for dense collocation. Then he said wrong, not good for dense collocation in every setting. So he sets it up one way and then he switches it to something else, basically shifting the goalpost here. Is a good front to back ratio good in every setting? There's always going to be an asterisk there. It depends. But generally speaking, having a good front to back ratio is a good indicator of a high performance antenna. It is one of the best ways, particularly with point to point dish antennas. Having a high front to back ratio is going to tell you a lot about the side lobe performance because the front to back ratio incorporates gain, which also tells you about antenna efficiency.
It's simply a misunderstanding. It's important to really get this right, because the next time you have a conversation about front-to-back ratio, you can be sure that if anyone is saying that high front-to-back ratio means an antenna is great for collocation, you know that the person is either misinformed, simply didn't go deep enough with the topic. High front-to-back ratio means that the back lobe is small. This is the lobe pointing in the opposite direction as the main lobe. It can also mean that the group of side lobes around the back lobe is small, depending on the definition or the way the front-to-back ratio was determined. The front-to-back ratio is very easy to understand. Looking at the radiation pattern of an antenna, in this example we show the pattern of a directional patch array. The front-to-back ratio is the difference between the gain of the main lobe and the gain of the back lobe, which is pointing backwards. In practice, front-to-back ratio is often determined based on the strongest side lobe, from a plus-minus 30-degree angle around the back lobe because of possible manufacturing, assembly, or material imperfections. Because of these imperfections, the back lobe might not just be a single lobe, but can be divided and fractured into several minor lobes around that direction. Nevertheless, back lobe is one of many side lobes antennas used in WISP industry typically have. So if back lobe is one out of many side lobes, then it's probably not so important. This is the typical error in
So it is important for comparison purposes. So if you're trying to compare two antennas, one has a good front to back ratio and one has a bad front to back ratio, you can tell about the quality of an antenna based on the front to back ratio. So while it doesn't give you a complete picture of every antenna in regards to side lobes, it gives you a good indication about an antenna's ability to focus energy in one direction relative to the amount of energy that leaks out the back.
Interpretation of front-to-back ratio. It doesn't say anything about all the other side lobes. When two antennas are exactly back-to-back, which, let's be honest, is quite a rare kind of scenario, high front-to-back ratio can help to decrease the interference level the radios see. But as I said before, typical antenna used with networks has a lot of side lobes, and the back lobe itself can be quite complex at the same time. As soon as there are more links on a tower or collocated antennas, are not exactly back to back, you are looking at noise issues coming your way because of all the other side lobes that these antennas have.
So again, the front to back ratio isn't going to give you a complete picture about an antenna, but it's going to give you a good idea about the antenna's ability to focus in a specific direction versus the amount of energy leaking out the back. And that ratio, you can then use that along with other things like gain, along with looking at the detailed antenna patterns to get an idea about the overall picture. You can use the Etsy mask, which they mentioned earlier in this presentation. They're going to be dismissing as well. But yeah, you need gain. You need to understand the front to back ratio. You need the Etsy mask. You need all of these things. You need the antenna pattern. That gives you an overall picture about the antenna. There's not one antenna parameter to rule them all. And if there was, it certainly wouldn't be this one.
High front to back ratio provides absolutely no protection in high noise environment.
So he just said front to back ratio provides you absolutely no protection in a high noise environment. And then on the slide here, it says high front to back ratio protects you only here. Which is it, no protection, or is it only protecting you in this way? In reality, if you have a good front to back ratio, then you're also likely to have a high quality antenna with lower side lobes as well. This is not an and or situation, but also these things are all related. So the ability of the antenna to focus in the forward direction is related to also the front to back ratio. And the front to back ratio is also related to side lobes. Although not necessarily, just generally speaking, yes. So generally speaking, an antenna with a high front to back ratio, a good front to back ratio, is also going to have suppressed side lobes.
So for urban and suburban areas with other wireless links in the neighborhood or even on the same tower, front to back ratio is irrelevant. These other links may be yours or competitors. Either way, they're using very similar hardware to yours, meaning their antennas most likely also have many side lobes that create noise, receive the noise, and anything in between through the rest of the side lobes.
So again, we're seeing noise coming from the side lobes. Magically, there's no noise in the main lobe. But noise comes in the side lobes, it comes in this back lobe, and it also comes in the main lobe. If you were to shape all of these into one giant main lobe, maybe you're going to have better noise resistance, maybe not. It just depends on the source of the noise.
Another parameter I want to mention is side lobe level. In practical life, its effect is similar to that of the front to back ratio. Let's have a look at the details of that. Side lobe level is the difference between the gain of the strongest side lobe and the main lobe. It is more useful than front to back ratio because it at least points out the strongest side lobe, which says a bit about antenna performance in high noise areas, but just a little bit really. If side lobe level is high, the strongest side lobe is close to having the gain of the main lobe, making it a very poor antenna for WISP networks. The issue with side lobe level is that it does not talk about all the side lobes an antenna has. Again,
so it does talk about all the rest of the side lobes that an antenna has because it's measuring the strongest side lobe. By measuring the strongest side lobe, you can know that all the rest of the side lobes are in fact not as strong as the strongest side lobe. Although it doesn't directly say anything about the other side lobes, it does say that they're going to be not as strong as the strongest side lobe. So you can get an idea about the performance of an antenna based on the side lobe level. And again, it's relative to, this is gain. Again, this is a gain measurement. It's the gain of the main lobe versus the gain of the strongest side lobe. Gain, again, is relative to a perfect isotropic radiator. So it is also built in measuring antenna efficiency as well. So that's why side lobe level is a very good antenna parameter for understanding the side lobe performance of an antenna, despite what RF element says here.
Ratio. It tells you what the strongest side lobe is at one frequency, but nothing about the rest of the side lobes throughout the useful bandwidth of an antenna.
That's not correct. So almost all antenna parameters are worst case numbers. They're the values of the worst case of the antenna across its designated frequency range. So in the case of side lobe level, it's the strongest side lobe relative to the weakest main lobe within the frequency range. So it's the worst case side lobe level is what you use for your data sheet. That lets the users of your antennas understand what to expect in worst case situations. They know that when they buy your antenna as per the data sheet, it's going to be better than what's described on the data sheet. RF Elements loves to confuse this. They love to confuse worst case antenna parameters versus average or versus typical versus best case antenna parameters. And a lot of times they'll take their typical antenna parameters, what they call typical, whatever that means, and then they'll compare that against their competitors' worst case values. They'll use that in a comparison table to show that their antennas are better than their competitors. They're just confused about this. So, as is the case of almost all antenna parameters, it's the worst case values that show up on the data sheets.
Which is the biggest issue with these metrics. In WISP networks, all side lobes of an antenna matter. To sum it up, not all antenna parameters are practically useful for WISP networks. It simply depends on the context an antenna is used in. In the end, it is up to the users and actually mainly the manufacturers to responsibly look at each antenna parameter and honestly evaluate whether it is useful in the framework of WISP networks or not. The conclusion for front-to-back ratio and side lobe level clearly says that these two are really not so important. They tell a very limited part of the story of the side lobes. And if you're wondering why WISP antenna manufacturers use them, show them in their data sheets and on, my guess would be it's simply a remnant of the times when these parameters were the only ones that were easy to determine and calculate without enough computational power.
So he says the reason why other WISP antenna vendors use the front to back ratio, side lobe level, is because we don't have enough computational power to determine beam efficiency. A lot of times I wonder about RF elements if they are incompetent or if they're malicious. It's really hard to tell the difference, but when I hear things like this, I really tend towards malicious. There's no way he could actually believe that. They just showed us what is involved in calculating the beam efficiency. It's simply a ratio of the energy in the main lobe versus the total energy radiated by the antenna. A ratio does not require a whole lot of computational power. When he says other antenna vendors must omit beam efficiency because they lack computational power, that makes me believe that they're grifters here. This is not them just not knowing what they're talking about. They know what they're talking about. They're purposely misrepresenting the truth.